Okay, so let's have a look at this one. Obviously, it's not terribly complex here. We have contestants in a snowshoe race move forward 10 meters and untie a series of knots. Okay, all right, so their first vector is 10 meters long. Okay, and then they move forward 5 meters and solve a puzzle. This is not a spectator sport, I don't think. Okay, so we got 5 meters. So when I draw that vector, I draw it on the head of the first, and I draw it about half as long as the 10-meter vector, okay, in order to represent it properly. And then they finally move 25 meters to the finish line. So that'll be my third vector, goes on the head of the first. Okay, it's roughly 5 times as long as the 5-meter vector. Okay, again, it doesn't have to be measured or exact as long as it's representative. Okay, now I've got a vector diagram of this very simple collinear race. Okay, so their total displacement here would be 40 meters forwards. Yeah, that's the one they give us forward in the question, right? So, okay, 40 meters forward. Okay, now here's where this will get tricky. When we start doing a lot of vector analysis, okay, you're always going to be converting directions to positives and negatives. Okay, north and south will be positive and negative reference to each other. Okay, what you have to remember is those represent other kinds of directions. When you're writing your final answer, you might have got negative on your calculator, but you have to write south on your paper. Okay, does that make sense? We always have to be able to convert back, okay, to what we were originally given in the question. Okay, so that one's pretty straightforward. Let's see here. Okay, let's see how you do with number 7. Okay, 7's a bit of an algebra trick. Okay, but the diagram can be helpful. Okay, so this car drives north 500 kilometers, then drives 3 sequential displacements south, so it turns around and comes back the other way, each of which is 50 kilometers longer than the previous one. In the end, the final position of the car is 50 kilometers north. Okay, what is the length of the 3 displacement vectors? Okay, it's a bit of an algebra trick. It's when I show you the solution, if you didn't get it, you're going to go facepalm. Okay, and that's all right. It's not a judgment on you. Okay, it's just kind of what happens because people are like, oh yeah, I know I should have thought of that. Okay, but most of the time, about 2/3 of people get it before, okay, I reveal the solution. So I'm going to give you a few minutes on that and see how you do. So they go north 500 kilometers, and then they come back in 3 sequential displacements until they get to this point here, 50 kilometers north of where they started. Each vector in that trip is 50 kilometers longer than the one before. Okay, so I'm going to have this one, which is x. How long is the next one? X plus 50. And this one is x plus what? 100. Okay? If each one, okay, is sequentially 50 kilometers longer than the one before, those are the lengths of the 3 vectors. Now you probably looked at that and going, so what good does that do me? I don't know what x is. But you can find it because the sum of these 3 vectors is 450 kilometers. Okay? We know that because the overall displacement is 50 kilometers north. Okay? So what I do is I say, all right, 450 kilometers equals x plus 50 plus x plus 100. Okay, can I take the numbers I know that are actual real numbers over to the other side? The 50 and the 100? I can. Okay, I'm just going to subtract them over to the other side because on this side I'm adding them. So 450, essentially minus 150, is 300. 300 equals x plus x plus x. Or could I write this? Is x plus x plus x 3x? Can I solve for x? Okay, so x is 100. Okay, so that means this one's 100 kilometers, this one's 150 kilometers, this one's 200 kilometers. 200 plus 150, okay, is 350 plus 100, 450. Algebra trick, agreed? I would never give you one like that on a test, okay? Because it's more of a math trick than it is a vector trick, okay? But it's still easier to do if you have the picture and you can label it like we were told to, right? Draw them tail to head and write what you know about them. Well, the first one I knew was x. And the next one I knew was x plus 50. And the next one I knew was x plus 100. And then I just put them in an equation. X plus 50 plus x plus 100, okay? Then I'm done. I can figure it out from there. Okay. Try number 9. Use a diagram for number 9. It's much easier than 7 was. Okay. We want to draw our vector diagram, but with collinear vectors that backtrack on themselves, it gets messy if you keep overlapping them, okay? So what we typically do for these ones is we go, okay, I dropped it from here, this is my initial position, it falls 10 meters, and then it rebounds 8. Then it falls back down to the floor, that's another 8, and then it rebounds 4. And then it falls back down, another 4, and then rebounds 2. And for whatever reason, that's where the question ends. I don't know why it doesn't keep going, but they guess they had to pick an end point. Okay, if you interpreted it that it ended up on the floor, your answer is going to be slightly different. But as long as your method is okay, and follow what I do here, your answer is fine if you interpret it differently. Okay, so if I want to get the total distance, what do I have to do with all these numbers?
Add them.
Add them. Distance is scalar. Doesn't matter whether it goes up or down, just how far did the ball travel while it was bouncing. Okay, so we got 10 plus 16 is 26, plus 4 is 30, plus 6 more is 36 meters. Okay, that's the distance. According to the way I interpreted the question, the total distance traveled. Okay, if you interpreted that it fell down another 2 and then stopped, okay, then your distance is going to be 38 meters. Okay, and that's fine. All right. Now, displacement-wise, if I started here, my initial position equals positive 10 meters. My final position, according to the way I interpreted this question, is here at positive 2 meters. So to get the displacement, I would go final position minus initial position. That would be 2 minus 10 or -8 meters. If you interpreted it this as though it ended up on the floor, then you got -10 meters. Okay? Everybody all right with that? Okay? Even though we solved for a scalar quantity, did the vector diagram help? It let us see all the things it did. Okay? Sometimes people miss some of those rebounds. Okay? And that's why I was saying it's so important to draw the diagram so that you know what happened, because it's easy to miss this rebound and that rebound. Okay? We have to make sure that those are included. All right. Okay, so I would like you to try this one. Write it down. Okay, this is the first one that's got a little bit of trig in it. Okay, not a lot. It's got like Pythagorean theorem and trig. Okay, so a camper leaves her tent to go to the lake. She walks 0.8 kilometers south, then 1.2 kilometers east, and then 0.3 kilometers north. Find her resultant displacement. Draw the diagram. Tail to head. Best advice I can give you. Okay, I'm going to put the diagram on here just in case you're stuck. Okay, so the first thing this person did was go 0.8 kilometers south. Okay, and then they went 1.2 kilometers east. And then they went 0.3 kilometers north. Okay, so this is their final position. This is their initial position. Agreed? All right. Think about the definition of displacement. Displacement is how much and in what direction you change your position. So if I wanted to draw a vector, an arrow on this graph to represent this person's total displacement, where would I draw it? From their initial position to where? To their final position. Okay, this line right here, I need blue. Okay, this line right here represents their total displacement. In order to find that, I'm going to need to know how far east did they go and how far north-south did they go. If I can figure out those things, I might know a couple of pieces of information about that line that would help me figure out how long that line is and what direction it's going. And you can find that from this diagram. Okay? I'll give you a few more minutes before I put 2 more lines on there that'll basically give it away. Okay? You got to figure out there's 2 more, and I wouldn't say they're solid lines. Okay? They might be dotted lines that should go on this graph. Okay, I'm going to put the 2 lines on here that basically give this thing away. In doing this trip, this person ends up 1.2 kilometers east of where they started. And they end up 0.5 meters south of where they started. Would you agree? Okay. Now that I know those 2 pieces of information, can I figure out how long arrow D is? Okay. I would just have to use Pythagorean theorem, yes? Now, displacement's a vector quantity. So I don't just want to find out how big D is. I also want to find what direction does D point. Now, if you drew this the other way, if you went like this, that's fine. You'll get the complementary angle to me. Okay, so let's walk through the rest of this and then I'll tell you why we do this question. Okay, so I've got to find out how big D is. I know the two sides of it. It's the hypotenuse of this right angle triangle. Okay, so my next step then is to go square root of a squared plus b squared. So 1.2 squared, okay, plus 0.5 squared. Oh, I don't need the brackets. Okay, and that gives me 1.3 kilometers. All right, so now I know how big that is. Okay. The other thing I need is the angle. So the way I drew this triangle, okay, I'm looking at 1.2 being the adjacent and 0.5 being the opposite. So theta will equal tan to the minus 1, although you could use any trig function you want because you know all three sides of the triangle, okay, of opposite 0.5 over adjacent 1.2. Times divided. All right, so I'm getting 23 degrees here. And that is south of east. Okay, if you got 67 degrees north of east, you're okay. Or sorry, east of south, sorry. You're okay. All right. So we would have two significant digits here. So our final answer would be that the person's overall displacement is 1.3 kilometers at 23 degrees south of east. As an aside, your calculator does need to be in degree mode for physics. Okay, if you're going back and forth between math and physics, you're going to be switching it between radians and degree a lot more than likely. Okay. All right, so here's why we do this question. It's to illustrate to you that any vector is made up of a horizontal component, in this case east, and a vertical component, in this case south. Okay? Any vector we get has a horizontal or an x component and a vertical or y component. Right? We can either, if we have both of those, use them to get the hypotenuse, or if we have the hypotenuse in an angle, we can use it to get the two sides. Okay? Just simple trigonometry. The reason that's important for us is it's how we add angled vectors together. In this one, all of your vectors were either north or east, okay, or south. Right? So they were perpendicular. You didn't have any crazy angles. Right? But where we're headed, okay, is doing a question like this. And I think I showed you this before. Okay, so if I have, let's say, this vector here, (500 meters north), okay, and then I have this vector here, okay, so this object does this. It goes 500 meters due north, and then it turns and travels 175 meters, 60 degrees south of east. Okay, where would I draw a line on this diagram that represents the total displacement of that object?
Initial position, final position?
Exactly, from initial position to final position. This final line that we draw is called the resultant. Okay? In this question, it's going to represent displacement. Okay? If these were velocity vectors, it would represent average velocity. If it was two force vectors, it would represent net force. Okay? We just call it the resultant because it can really be anything. Okay? Now, this resultant also has a horizontal x component and a vertical component y, and a vector and a magnitude, just like everything else in the diagram. Okay, so here's what I do in a question like this. Okay, I figure out over the whole trip how far north or south did the object go. just like in those simple questions we had with like the garbage truck and the bus and all of those, right? It went this far north and then it went this far south and we figured out what the total displacement was. We're doing the same thing here, okay? This object goes 500 meters north and then it does this. When it does this, does it also go south? It goes east and south at the same time. And I can figure out how much east and south it goes using trig. Okay, so this green vector also has an x component and a y component. Now, just looking at this diagram, how do green x and purple x relate to each other? Because I actually did a pretty good job of drawing that diagram to scale.
They're the same length?
They're the same length, okay? In this trip, the object only went east during the second part of the trip. So its total x or east component is that number. Okay, that's it, because it didn't go east in the first part, it just went due north. Okay? Now, if I want to find purple y, would purple y be the sum of 500 and whatever green y is? Assuming I made green y negative because it's south, would that be okay? Okay, that is vector component addition. If I find the components, that is the north, the x and the y for all the vectors, and I add them all together, I'll find out what my total x and total y are. And then I'll have a right angle triangle for my overall resultant, in this case, displacement. Okay? So as long as you understand that kind of that method, the rest of it is just trig. It's just punching numbers into your calculator. Okay? The trickiest part of this is drawing the diagram and knowing what lines you have to calculate. The calculating part is pretty foolproof. Okay? As long as you know SOHCAHTOA, you're good. Okay? That's all you need to know. And a squared plus b squared equals c squared. Okay? All right. So on this one here then, okay, if I wanted to complete this, if I want to find x, and I know the hypotenuse and this angle, what trig function would I use to find x? Cos. Okay? Because x is adjacent to the 60-degree angle, and I know the hypotenuse. Okay? Cos is adjacent over hypotenuse. Right? So x over 175 adjacent over hypotenuse equals the cos of 60 degrees. Okay, the cos of theta, in this case 60 degrees, equals adjacent over hypotenuse. Everybody okay with that? So how do I get x? What do I have to do with the 175?
Cross multiply.
Right, cross multiply. Right now I'm dividing by 175. I want to move it over to the other side to isolate x. I multiply. Okay, so I'm going to multiply the 175 over to this side. That's going to solve for x. Okay, so I'm going to go 175 times the cos of 60. Oh, I can't believe I punched that in. The cos of 60 is 0.5. Okay, 87.5. Okay, and I always put a direction on that. Okay, this object went 87.5 meters east. Okay, what trig function will I use to find y? In relation to the 60-degree angle, is y opposite or adjacent? It's opposite, right? It's not touching the 60. That makes it opposite. If it's adjacent, it's touching the arc for the 60. This isn't touching the arc. Okay, so y is opposite. So that means that y, the opposite side, over 175, the hypotenuse, equals the sine of 60. Right? Sine of theta equals opposite over adjacent, or sorry, over hypotenuse. Okay? So if I want to get y, I just multiply both sides by 175. Okay, 151.55. Okay. So can I find purple X and purple Y now? I absolutely can. We already said purple X is the same as green X, so purple X is 87.5 meters. Okay. Y is going to be the sum of 500 north plus 151.55 south. Okay, so it's 348.45. I'm going to keep all those numbers in my calculator, guys. I'm just too lazy to write them. Okay. Do I have enough information to complete that triangle? The purple triangle? I do. Okay. And all I've done is figure out how far X horizontally and how far vertically this thing went during each section, and then over the total. Okay. So I'm going to do Pythagorean theorem to get what D is. All right, so D is 359.26 meters. And I need to find theta. Since I know all three sides, I can use any trig function I want, but my favorite is tan. Okay, so tan to the minus 1 of the opposite side, 348.45, divided by the adjacent side, 87.5. Would it be okay if you drew the triangle this way? Would that be okay too? Sides are the same. Okay. All right, so second tan of 348 divided by 87.5. All right, so that angle there is going to be 75.9. I did not do a very good job of drawing this to scale. Okay, 75 degrees should be like this, okay, which means that side should be a lot longer. I drew that Y way too long. Okay, well, actually I probably drew the 175 way too long. Okay. All right, so there's the importance of scale. We talked about that the other day, right? My scale really kind of screwed up how my diagram looks. Okay, so 75 degrees. And for me, what's the direction on that?
North of east.
North of east. Okay, my arc touches east, so the 75 degrees is measured of east or from east, and it goes north of it, north of east. Okay, so. Okay, last semester's unit exam. I don't remember if the numbers were exactly the same, but it was one north and one south of east, just like that. Okay, we're gonna do way harder ones than that in class, but that was the exam question. Okay, now right now you're probably going, oh crap. Okay, but trust me, once we do some of the ones that are really crazy, you're gonna look back on this one and go, oh man, that's so easy. Okay, now here's the thing, I don't want you to get discouraged. Okay, when you first start out doing this, it takes a really long time to do a question. Okay, but once you learn the steps, here's the good news, the steps are the same for every vector addition question. Okay, once you learn those steps, then it's just a matter of repetition. Okay, is there a lot of trig? Yep, but I think I told you that before. Okay, so it's a matter of just getting in the habit, getting the method down, and then you're gonna be good. Okay. All right, I'm gonna give you about, no, we don't really have time for a break now. Sorry guys, I went too long on that one. Okay, let's look at kind of a breakdown of what we did on that question. Okay, I kind of showed you the final product without showing you kind of how we get there, okay, kind of thing. So, vector components and vector component addition are what we're going to use basically for the rest of this unit and unit 2, okay? Because everything that's important in these units are vector quantities: displacement, velocity, acceleration, and force. Okay, so there's going to be a lot of vector stuff going forward here. Okay, so the first thing we have to do is learn how to resolve a vector into its components. Okay, now you're probably thinking that and going, Coderre's speaking Greek. I don't know what that means. Okay, except it's exactly what we did here when we found green x and green y. We broke down that 175 meter long vector pointing 60 degrees south of east into its horizontal component and its vertical component. Okay? All we do when we're finding vector components is we're taking a vector and looking at how much over it goes and how far up or down it goes. Okay? It's horizontal and vertical components. Okay? So basically every time you're going to do a cos and a sine, okay, calculation and get the two sides. Okay? All right, and then learn how to use vector components to add vector quantities that are not collinear or perpendicular. That's what we did on that question. Okay, we found those components and then we used them to figure out how far in total the object went north-south and how far in total it went east-west. Okay, then we drew the triangle and solved. Okay, those are always the steps. All right, so if we want to break down a vector into its components, as I said before, what we're doing is figuring out how far it moves horizontally and in what direction, and how far it moves vertically and in what direction. And all we're doing to get that is using the information given about that vector. Okay? They're going to tell us its magnitude, they're going to tell us its direction, because they have to. Okay? It's a vector quantity. It has those two properties. It always has a magnitude, it always has a direction. We're always going to know those two things. Okay? Since we do, okay, then we're always going to be able to figure out what its x component is and what its y component is. How far over, how far up or down the object goes during that vector. Okay? So if I wanted to find ax, and I knew what a was, let's just say that a is 200 meters and theta is 30 degrees. How would I find x? How would I find ax? Okay, I know the hypotenuse, yes? And I know the angle. Okay, so which side is x? Adjacent or opposite?
Adjacent.
Adjacent. Okay, now if you're confused, if you're hearing me say which side's adjacent, which side's opposite, and going, I don't know, okay, here's how we tell. Okay, when we have this angle arc here, okay, the one that indicates there's an angle here, okay, whatever direction that touches is the adjacent side. Okay, it's beside that angle, okay, or adjacent to that angle. Okay, the other side doesn't touch it at all. That's the opposite. It is opposite this angle. It's not touching it. Does that sort of make sense? That's how we tell the difference. Okay? All right, so if I'm looking for AX, and I've decided that AX is the adjacent side, and I know the hypotenuse and the angle, what trig function am I using? Sine, cosine, or tan? Good. You might want to write this down somewhere. That's how you know.
Cos.
I would use cos, because I'm looking for the adjacent side, and I have the hypotenuse, okay, and the angle. All right, so I would want to use this one because cos is adjacent divided by hypotenuse. That's what I have, and that's what I'm looking for. Right? So to find AX would simply be, okay, understanding that the cos of 30 degrees equals AX, the adjacent side, divided by 200 meters. Okay? So to find AX, I would just multiply both sides by 200 meters. Very similar thing to find Y, except instead of cos, I'm going to use which one? Okay.
Sine.
Sine. It's the opposite side. Okay? If I use cosine to find the adjacent side, I'm going to use sine to find the opposite side. Okay? That's just one you're going to have. That'll come with repetition. Okay, if right now you're going, God, I don't remember, how do I figure this out? Okay, it'll come with repetition, because we're gonna do lots of these. Okay, we spend like a week and a half on this. Okay? All right. Okay, so this is what we were just talking about there a minute ago. Okay, if I wanted to find the adjacent side, it would be the hypotenuse A times the cosine of theta. Okay, that would give me AX. To find the opposite side, I'd take A, the hypotenuse, and multiply it by the sine of theta. Okay, that would get me the opposite side. Okay. Okay, so if we've got this one here, okay, I want you guys to find X and Y. Okay, D is 175 meters. Theta is 50 degrees. Okay, see if you can find X and Y.